I'm gonna write these down. If you already have these written down, you're good. I just want to write them down again.
So it goes to x minus h plus 1. Right, 1, not 0. Answer 0. He's obviously much better.
Yeah, we definitely did not tour class. I was like, are you gonna be on more specific? Yeah, but that's like the plan. She's gonna be on the 21st.
One of the reasons that was that.
Okay. So I don't have I know the last couple days I haven't had handouts for notes and stuff, and that's just because I just been swamped. Matter of fact, I'm surprised I've been organized enough throughout the rest previously in the year to have this stuff. So so there's nothing to hand out. These are just straight up notes. I know you guys already have these, so you don't need to write that down. All we're doing today is we're just introducing energy into simple harmonic motion, which we've already kind of done already. So all this stuff is reviewed, bringing it back, we're going to solve some problems, regular thin group quiz and a regular quiz today. I just got it's got a whole bunch of other things with Science Olympiad and stuff going on. I got other things on my mind here, I guess. All right. So what we're introducing today is the kinetic energy and just energy in general to simple harmonic motion. Okay, and again, it's all review stuff. It's stuff we should already know. Okay, so these are the equations for the solution to that second order differential equation that describe the position, the velocity, and the acceleration of an object undergoing simple harmonic motion. Okay, so I'm going to give you a couple more derivations to help prove certain things. So make sure you have these derivations written down though. Okay, so the first thing is we're going to write down the kinetic energy equation. Okay, that apply to simple harmonic motion. All right, so the kinetic energy equation would be 1/2 mv squared. And because we already have the equation for velocity, we just plug in the velocity function and square it. Okay, so that would be 1/2 m. Okay, so everything else would just be squared there. M omega squared, a squared, sine squared, omega t plus phi. Okay, and then the internal energy equation would be 1/2 kx squared. All right, and that would just be the 1/2 with the k. Hey, Niraj. There you go. So adorable. Thank you.
That's a great sign. See, I can do normal.
Not buying it.
No, I was so excited. Everybody's like, oh, I walk in, everybody's like, go away.
I was going to say something, Sebastian, but I'm going to keep from it. Okay. So a squared cosine squared omega t plus phi. Now, the mechanical energy, how do I get the mechanical energy if I know the kinetic energy and the potential energy? What's the mechanical energy equal to? You know, it's been a while. So remember? No, it's a two together. Yeah, we just add the two together. So the mechanical energy or the total energy. Let me write out the whole word mechanical here.
It was on the test.
Was it?
Yeah.
Mechanical. Okay, so that's equal to the kinetic plus the potential. Okay, and so if we look at this, I think you'll notice something here. What did happen to my omega there? A squared And then I've got sine squared. That's weird. I just now realized this. What happens to the omega out front here? Omega squared 1/2 k. Huh. Omega t plus phi. Oh, I did the sine one first. Plus cosine squared omega t plus phi. Okay, and what does that look familiar to? Well, like, what is this? What is this? What does that become right there? Okay.
M omega squared equals k.
What happened to everything?
Okay. Yeah. So.
M omega squared now equals k, I guess.
Oh, that's right. Yeah, that's right. That's the
We're all screwed up in this. I don't think I just have to make it.
Okay. All right, listen up. We've got this part. Okay. Okay, listen up. Thank you. We've got, so this is the part that we already know. Okay. And so we've got to, I need to erase that. Okay. So that's the part that we already know. And we're just plugging those into the kinetic energy and the potential energy equations. All right. Now, the k squared, here's what happens with this from this derivation. So remember last time we proved that omega was equal to the square root of k over m. All right. So if I square both sides, I get omega squared is equal to k over m. So if I solve that just for k, I get k is equal to omega squared, or m omega squared. Okay, so this part here, this m omega squared, is equivalent to k. So that's what we had to prove there. Oh, thank you. Thank you very much. Okay, so that's how we get the ka squared factor out. All right, and as Garrett was saying, this part is equal to 1. So therefore, the mechanical energy we can write out, or the total energy we can write out as being equal to 1/2 ka squared. All right. Now, your book points out something that we kind of already know from solving these problems, for solving for the velocity. We can prove that because this is true, all right, and that the mechanical energy
is the radius, or A is the x part of it.
Yeah, it's the amplitude. It's the maximum amplitude. Okay. So, and you guys will see this you'll see this proof on that sheet that I handed out. Okay. That because this is equal to 1/2 mv squared. This is equal to 1/2 mv squared. Plus 1/2 kx squared. Okay, and that's equal to 1/2 ka squared is the total energy. All right, so the difference here is that this x is the x anywhere in the object's motion, and this a is the amplitude. All right, so we can solve this equation. Again, this is on that sheet of paper that I handed out to you. It's plus or minus the square root of k over m a squared minus x squared, and and we can take out the k over m because that's equal to omega, and that's plus or minus as well. Square root of a squared minus x squared. Okay, so let me just go over with you why some so this k here would be the let me make sure, yeah. Okay, so that k would be kinetic energy. These these K's here would be the spring constant. All right. So that K in this equation is the spring constant.
So is lowercase
Yeah, it's supposed to be, but I draw them pretty similar. Okay. So like the K.
under even K?
So the best way of probably explaining it and all of that is really the only K that I have up there that is the kinetic energy is this one right here, right? Are there any other Ks I have up there that are kinetic energies? Oh, okay. Right there. And where else? That the only ones?
K squared is the spring constant.
Yes. Yes. So this K is the one for the spring constant. All right. Now, to explain the difference between that A and that X is like this. So if I've got this spring, okay, if the spring's connected to a wall and it's connected to some mass, this object that goes back and forth, this distance that it goes would be A, okay, and negative A on either side, okay. So that's what A is defined as. It's this maximum amplitude, okay. Whereas X is everything, including A, on either side. Does that make sense?
Are there any equations for A?
Yeah, and I'll basically this relationship for A ends up being pretty important here. This is an equation you end up using that I was kind of surprised. So this equation here you end up using, and make sure you remember that omega here, this actually comes up in the Weber sign, that omega is equal to the square root of K over M. Okay, so yeah, that does come up. All right. Okay, so how do we apply this? Here's how we go about going to an example. So I want to go to this example. So draw this out. I've got on a once again I got this long spring. Okay, it's connected to a mass, and it can go out as far as an amplitude of 0.040 meters out to this distance. Okay, and it's going to go back and forth that same value over here, negative 0.040 meters. Okay. And here are the 4 things I want us to figure out. I want us to figure out the total energy, okay, or the mechanical energy, the speed at 0.010 meters from the equilibrium. So this location here, this location there, that would be 0 meters. Okay, I want to know the kinetic energy and the elastic potential energy also at that location. Okay, so those are the 4 things I want to calculate. All right, so the total energy, if it starts off, if the object starts off where I've stretched it all the way out to, let me use a different color here. Ink color, let me go to a dark blue. So let's say that the object gets all the way out to here. Okay, so its mass is all the way out to here. The spring has somehow elongated so that it's gone out to there. Okay, and it's at the location 0.040 meters. If I use my energy model, okay, at that location, if I call that my location, right, I've got the mass, I've got the spring. I guess I can include the Earth even though it's not part of my energy model, or it doesn't have to be part of my energy model. At this beginning location, okay, so let's call this the initial position. So at my initial position, if I'm going to look at the initial kinetic and initial potential, how would I fill that out? Okay, it would be all potential. Okay, All right. So if that's all potential at the beginning, what can I say about my total energy from in question number 1 here? Yeah, the potential energy would be equal to my total mechanical energy, right? So my total mechanical energy would be equal to my potential energy. And I can set that equal to that equation that we proved, the 1/2 Ka squared. Okay, so where we've got 1/2 and K is equal to 200 newtons per meter. Oh, okay, I didn't give you guys that. Oh, yeah, so K is 200 newtons per meter, and also the mass, that's a spring constant, by the way, 200 newtons per meter. And the mass, let's make it 0.1 kilograms. Okay. All right, and so we would plug in what would I plug in here for the amplitude? Okay, 0.040 meters. I'm going to square that. Does anyone put that in their calculator? Okay, 0.10, 0.160 or 0.0?
The whole thing is 0.16 though.
Okay. All right. So that's my total mechanical energy right here at the beginning, and at any time afterwards. Okay. So this value here has to be a constant throughout the entire movement of that object, no matter where it is. Okay, the kinetic and potential have to always equal that value. All right. Number 2 says, what's the speed at 0.010 meters? Okay, so let's call that the next position. So for my kinetic energy and my potential energy, I would have to split that up. All right. So some values, we're not sure, but these two have to add up to that. Okay? So in writing out that equation, here's what happens. Okay? So I've got, if I compare these two values, I get the initial, all I get in the beginning is initial potential energy is equal to the final kinetic plus the final potential. All right, so again, we could just use our energy model to solve a lot of these problems. So I know at the beginning I got 1/2 Ka squared, but again, that's just the same as x squared, is equal to 1/2 mv squared plus 1/2 kx squared. Now, from our energy model, we get the equation for the velocity. All right, the velocity is equal to the square root of K over M, A squared minus X squared. So again, this equation doesn't need to be memorized. It comes out of the energy model. All right, so what's the value of my spring constant?
200.
Okay, so I have 200. My mass is what? 0.1. Okay, my amplitude, which was my original length, 0.04 squared minus the, at that location, 0.010. I guess I didn't write that other significant figure in there. That's okay. All right, and I get a velocity. You want to calculate this out for me?
1.732.
Thank you. I'll go 1.73 meters per second. Okay. And then for number 3, how would I go about finding the kinetic energy at that point? What would I use there? Yeah. Good. 1/2 mv squared. Okay, so I would plug in my mass, which would be 0.1 kilograms. My velocity, which I got from right there, 1.73 meters per second, and square that. That ends up, Ricky, you got that yet?
0.15.
Okay, I'll go up to another significant figure there. Okay, and number 4 asks, what's the potential energy at that location? So how would I go about figuring that out? Good. So my total mechanical energy, like we said, should be equal to the kinetic energy and the potential. Okay, so my potential energy there would be equal to the total mechanical, or mechanical minus the kinetic, and that's what we would expect from our energy model. That would equal 0.60 joules minus 0.150 joules, and that's 0.010 joules. Okay? All right, so again, we could just use the energy model in solving these problems, even though